we're going to add one more thing, one more simple law. The one more simple law is Avogadro's law. Avogadro's law just says the volume is proportional to the amount of particles, or the number of particles here, or the amount of gas. And so the more particles, the more volume you have. And so let's sum up Avogadro's law here visually. And so the volume is directly proportional to the volume. And so let's say 3 particles takes up this volume. Well, 6 particles will take up twice the volume. 9 particles will take up 3 times the volume. So do you see it's double the number of particles, double the volume, triple the number of particles, we triple the volume. So the volume and the number of particles are directly proportional. And the number of particles is directly proportional to the number of moles. So we can do stoichiometry with this as well. This makes stoichiometry really easy. It makes stoichiometry really easy because the mole ratio is also the particle ratio. So if we have O2 plus 2H2, these are gases, this is gas. And this is going to form 2 H2Os, but normally I write 2 H2O liquid. In this case, I'm going to write 2 H2O gas. So we're going to have to heat this up. And so there are different ways that we can do it. Avogadro's law says this: the mole ratio is the same as the volume ratio. And so 1 liter of O2 would require 2 liters of H2. So if I take 1 liter of O2 and 2 liters of H2, I'm going to form how many liters of H2O gas? 2 liters. So it's a 1 to 2 to 2 ratio, both in moles and in volume, if everything's a gas. It's Avogadro's law. And so we can do something simple here. Rather than taking 1 liter, let's take 50 milliliters. If I take 50 milliliters of O2, how many milliliters of H2 will I need? Twice as much, so it'll be 100 milliliters. And how many milliliters of the water gas will I form? 100 milliliters. And so this is Avogadro's law. 1 volume of O2 requires 2 volumes of H2, which forms 2 volumes of water, whatever the volume is. It could be gallons, 1 gallon, 2 gallons, 2 gallons. It's the mole ratio is the same as the volume ratio according to Avogadro. And so now these are the simple laws we have. The simple laws we have are Charles' law, Boyle's law, and Avogadro's law. If we combine these, we get the ideal gas law. In fact, with the ideal gas law, we can pretty much supplant the simple gas laws. We don't even need those anymore. We just have one gas law, the ideal gas law. And so this is all gas laws wrapped up into one. All gas laws wrapped up into one is the ideal gas law. There are 2 forms of the ideal gas law that we're going to use. And ideal gas law is just some kind of empirical deal here. The 2 forms of the ideal gas law that we're going to use is this one, PV equals nRT, where R is called the universal gas constant, or just the gas constant. Or P1 V1 over N1 P1 is equal to P2 V2 over N2 T2, which is equal to R, which is a constant. And so this ratio is always the same. So if we change something, the others have to compensate for that change. That is, if we increase the numerator, the denominator has to compensate for the increase in the numerator. So it'll have to increase as well. And so these are the 2 forms of the ideal gas law that we're going to use. So all we're going to do is we're going to do some calculations using these equations. This is your standard calculation. We need 4 things to characterize a gas. So if I have a gas sample, what do I want to know about that gas sample in terms of physical? Obviously, I'd like to know its chemical properties, but we don't even need to know that for right now. We need to know the pressure of the gas, the volume of the gas, how much gas we have in there, and the temperature of that gas. How much gas we have in there is the number of moles. And if we know those 4 things, then we fully characterize the physical properties of that gas. And so let's take a look at the sample problem. A 0.1000 mole sample of helium. And so the volume here we have N, 0.1000 moles. 0.1000 1,000 moles. This gas is helium, so the ideal gas law doesn't tell us about the chemical properties. It just tells us about the physical characteristics of the physical properties of the gas. So N is 0.1000. It's heated to 298.15. T is 298.15 Kelvin. V, the volume is adjusted to 4.600 liters, 4.600 liters. And P, we don't know what the pressure is. But if we know 3 of the 4, we can figure out the 4th from the ideal gas law. And so what we'll do is we'll just simplify the ideal gas law. P is equal to nRT over V. And so the pressure is going to equal the number of moles, 0.1000 moles. Oh, do I have the pressure? Oh, I have the pressure. So what's unknown? If I know all of these, what's unknown? The R. All right. The pressure is 0.5319 atmospheres. Normally we know the R because we memorize it. But here we're just going to calculate what that constant is. So this is the R constant over here, and that's the same as the R constant over here. It's the gas constant. The gas constant we can get by taking the pressure times the volume over R, N times T. N times T. So the pressure is 0.5319 atmospheres. The volume is 4.600 liters. N is 0.1000 moles. And T is 298.15 Kelvin. And so what this is going to give us is going to give us 0.082064 liters times atmosphere divided by mole times Kelvin. I just swap liters atmospheres because normally I memorize it that way, liters atmospheres. So this is the gas constant. Now what we do is we do a whole bunch of these experiments and figure out the gas constant empirically. You just don't do one experiment to determine R. You do multiple experiments and then you average those experiments. Why do you do multiple experiments and average them? Because we worry about something called error, random error. And that random error can be a little high, a little low, and it's going to be random error. If we look at the average over a large number of experiments, it's a little different than this. I got 0.082064. Here, the accepted value is 0.082057,338, on and on. What's going on? But you should memorize it. What should you memorize? You should memorize R. And so start memorizing this. Memorize that R is equal to 0.08206 liters atmosphere per mole Kelvin. We use this number all the time when we do calculations. So when we use it so much, it's not so hard to memorize. All right, so what did they get? They got the same thing, 0.08206 atmospheres liters per mole Kelvin. All right, so this is the most common use. We solve it for a single variable that's unknown. There are other more fancy uses for that. So a variation, we'll talk about all the variations that we're going to do here, starting with this one. But we'll do that next time.